I surely hope you talk about chemistry in calc class. Just saying. All right. Ladies and gentlemen, good morning. So I want to start today with some warm-up that will just refresh us on what we've done the last couple of days. So in this handy-dandy little packet that was on your desk to greet you, I have on the first 3 pages, problems circled. Can we tackle those problems now, please? Encourage you to get out a calculator. You guys are amazing at mental math, but you know you can rely on a calculator if needed. If you're stumped on one, please ask me or skip it until we awaken ourselves and so on. Yeah, the ones that are circled are the ones. You can definitely check in with each other. Check in with me as you're going if you want. I'm just going to do like next year. And then you measure the speed. It's not right for this. Yeah. It's definitely one of them. To keep this confident. What happened to them? By that shot, if I'm not this by 3, by 4. So what that means in the grade law, there's nothing. So it was second motion, if I double this, it would be 2 squared, then the rate would be 4. So if it's not a rate, if I double this, keep everything else constant, see if I multiply that by 2, well, that will be and see that it's 5, but it's by 5, because it's 5, because it's 5 to the first. Okay, so that's what it means to be reversed. So that narrows it down to these. So, yeah. Okay. Yeah. Given data from the experiment, and what was changed was the concentration of English. So, yeah, put one in and then just measure the rate of production of this right from the start. We're gonna do another experiment where we're doing one of these. And I don't know about you, but it's like double it, cut it in half, triple it. It's not gonna be the. So if you double this, because this is constant. What happens to the small students? Okay, so here is whatever we do, this concentration of that rate. If everything else is constant, K isn't changing, we're changing reaction. And the other thing is a constant. So we just look at whatever you do, today's case is double. But how? Where if it would, if you double this and it's quadruple, it'd be seconds. If you double this and the rate didn't change, it'd be 0.
Yeah, you're right. I have.
So we're looking to add, yeah, is that, okay. No, so what you wanna do, so from there to there, that's constant, and I double, so that improves.
Yeah.
Okay, well, shoot, I wouldn't compare 1 and 3. Unless I don't have any other option, because I'm doubling that, but I'm also quadrupling that. What about 2? This is constant. So that impact on the variable. That's what you, yes. Yes. It's not too much of a job. Okay, for sure. Phone. But
Oh, yes.
all right, very good.
Thank you.
You're welcome. Sorry about that. Tangled mess.
Matter what you go, as long as it's the same. So if you do.
It's the feel in the so we're ordering. What shows us what colors we have. Well, do an experiment and you just do concentrations and measure the initial rate of production or something. Then you're going to do another experiment where you're going to change just one of the concentration. So keeping this constant is double, and we're going to choose like increase it by 4 double. So if you double and there's any change on rate, it's because of that. Now, if you kept this constant, not double, this didn't change. Well, the rate is the same, that means that's zero order. Because if you're doubling this, it's zero. But what's going on here? So you're doubling.
So it's just the number. That's just.
So.
I thought that's okay. So I do the best. So then you use this. So I should this. I just did display these.
So. It's with cells, they're just like this. The rate change forward. Then what is your explanation? So it's like, if you change and it has that same impact on the rate, then it's first one.
So.
If you double this and it's double. Those are going to be our options. Zero, well, zero first, second, half. Yeah.
23 base. So this one actually.
We'll take 30 more seconds and then start to chat.
It's square. So, so the 2.30 times that is negative, right?
Okay, ladies and gentlemen, if I could interrupt us, get our attention. Ask whatever you need. Do not let a question go unanswered. Please, please, please. All right, this is new territory for us, so please. 2C. Hands down. Now, the most common orders are, well, remember I gave it to us in kind of order. The most common order of a reactant is first, then second order, then zero order, then 1/2. And then we can also have third and 1/3, but those are pretty uncommon. And we'll learn why soon, why that's the most common and then that. Do we get it from the coefficient of the balance equation? No. In fact, I think the first one you do on the next page, you find that NO2 is first order, but in the equation, there's a coefficient of 2. So no. And second order doesn't mean you have 2 reactants. It's the impact of that reactant on rate. Good? Definitely good. All right. So 3 is D. Can you talk about it? Okay. We are given the rate law. The rate law. So I can see that, okay, M and N are my reactants, and M is only first order and N is second order. Okay, so I start with this is my molarity of each. Oh, nice. And then, oh, I am doubling each, and it's asking me for the impact on rate. So what we're doing is taking this from, let's say, 1 molar to 2 molar. So I'm doubling this. So that will be 2 to the first power. Here, I'm doubling that as well, but this is to the second order. And so if I double this, and if I double this, but this gets squared, well, then it's going to double and quadruple. And so it's going to have an 8-fold impact on the rate. Yeah. Does that make sense? Bryce, what if your industrial manager came to you and said, okay, you can either increase the amount of M or increase the amount of N. You can't do both. What would be more worth your time to speed up the reaction? So do you see, you want to put your money where you get the bigger impact. So that could be something that this is useful for. Okay. All right. So then anytime you're given different experiments, and what's different is we're varying the concentration of reactants and then measuring the rate right off the bat initially. It's a method of initial rate. And we should get B for 7. 8. If it is 0 order in hydroxide, now it doesn't mean like it's not important. We need it there. It has to be there to get product. But 0 order, it doesn't impact the speed of the reaction. We just need it there. And we'll talk today about why that, when that can happen. So they're saying you're going to do the reaction, but you're just increasing the amount of hydroxide. Well, it's 0 order. It's not going to change the rate. You did not change temperature. You did not change the reaction. C is your choice. Remember, K is constant with temperature and reaction. Because hydroxide 0 order doesn't matter. As long as we just have it there. All right. And then, if you're not asked to show work, we can just go ahead and conclude. Did I drop the ball now? Second order. Hold on 1 second. Second order with ClO2. It is first order with hydroxide. Yes. So rate equals K, ClO2, second order, hydroxide, first order. And then, Mackenzie, what did you get for the value and the units of lowercase k? Am I good with how I wrote it? Yeah. Mackenzie, if you could look back at that, and if you want me to go through that, I definitely will. If anyone wants me to go through, totally fine. First, can I say that the magnitude of lowercase k, it doesn't really mean a whole lot now. All that we need to make sure we understand is that lowercase k will always be positive, always be positive, always be positive. That's all we need to know now. So if it's 230 or 23.0 or 0.230, doesn't matter. Okay, so I'm going to take my rate and then divide it by this concentration, of course, squared, and then this to the first. All right. My rate, mole per liter second, over mole per liter squared, mole per liter. Okay, whatever order makes sense to you. So this is how my brain understands it. I know this mole and this mole will cancel each other. And I know this liter and that liter will cancel. Okay, so what I have is just a per second in the numerator, or second to the -1. And then in my denominator, I have mole squared per liter squared. But to refine this down, I can do the inverse of that, right? Or flip the, I don't know what words you guys use. But what will end up happening is we get liter squared in the numerator second. And it doesn't matter. Is that, I didn't use good words. Go ahead, Tyler. No problem at all. It's weird, right? Because we have all fractions. Okay. So if I wanted to like really move where all my numerator and denominators are in reference to the main fraction. Makes sense? Okay, then I have mole in my numerator, but then won't also the denominator of the denominator becomes the numerator. And so this will be liter squared times liter, which is liter cubed. Okay, but I have a liter second in the bottom here. And then I'm going to have mole cubed. So I just get rid of one of these. So it would be mole squared and one of these. I don't know. What order? Emily, what order do you think through that? I'm not sure how you guys, what terminology you guys use. So can you see that that is perfect? Tyler, did that give you what you needed? Forgive me. I know I'm not using the right math terms. I don't think I am. Any other questions or concerns? And remember, I showed you yesterday, like, if you want to check yourself, or this is a way you could do it. If you know it's third order overall, you know it's third order, well, you know that rate is mole per liter, whatever unit of time. Okay, we need that. Well, this is going to be mole squared per liter squared. And then this is going to be mole per liter. Well, what do we need the units of K to be so that things will cancel? So you just have that as your ending rate unit. So you could approach it that way too. Questions? So we never have to know, but this is called the method of initial rates. We have to know if we're given this kind of data, where to go with it. Okay. Ready to move on. I know we are. So into our unit packets, and we'll come back to address some questions on this. All right. So we left off with the problem on page 7. Okay. You don't have to write this down, but just to show where we're going next. So we know we have the rate expression. So if my reaction is 2A plus B yields 3C, I'm being, of course, so generic here. Well, I could express the rate in terms of the change in concentration of A per unit of time, or this, yeah? If I'm given the value of 1, because I have the balance equation, I can get the values of the other. Rate expression. And then we have the rate law. And that'll be to some, or to some. This reaction is, or this unit is all about the speed of a reaction, how fast a reaction happens. This is really useful. But what variable, if we're talking about speed of the reaction, how long a reaction takes, what variable are we kind of missing here? So what can we solve this for? Well, I could plug in concentrations if I know K to get rate. If I know these, plug in rate to get K. If I know all the others, I could find the concentration. of either reactant. Bryce. Where's T? Never fear, we figured out a way. So from this point onward, when we talk about the integrated rate law, we are just considering one reactant at a time. Of course, a lot of reactions don't just have one reactant, but we're just going to consider that for our first exposure. So we have rate expression, rate law, really differential rate law, but now integrated rate law. All right, so page 8. So in this reaction, experiment showed that this reaction is first order in N2O5. So our rate law, would be this. Okay, great. Where's our element of time? So I believe it's 575 or something page in your Zumdahl book that shows the derivation. You don't have to derive or integrate. We just have to know what equation to use when. And we don't have to memorize them. I'll give them. So if we go ahead and integrate this per being first order, we get this. That is the reaction or the equation if our reactant is first order. So what does all this stuff mean? I'm just going to be generic if you don't mind. Okay, so I see bracket A not. What's the difference? You guys know. Take it away, sir. So this is our initial, we know square brackets are concentration and molarity. Yeah. So this is the initial start concentration of A or wherever I'm comparing. And then this is the concentration of A at time T. So the way that equation has come about is to make these related. And then, of course, we have our rate constant there. Be careful, do not forget the negative. Well, if you were asked to simplify this, Michael, what would you do? Because that seems like a big old lot of stuff. Could you simplify this? Sure. Would it be okay? We have the choice to subtract natural log of A naught from both sides or natural log of A from both sides and then add KT. So I know when I'm problem solving, sometimes, not all the time, but sometimes I forget if there's a negative there. So if I have a choice to make it positive, I'm going to do that. So KT is equal to, and then it'll be natural log of A naught minus natural log of A. And then, can you do anything from there? Oh, I think you said, right? Yeah. Yeah. Or if, and then it'll be just opposite. Either is totally fine. Either is totally fine. All right. Okay. Why this big old clunky-ish equation? I know you see it. So why didn't I just say when we integrate a first order reactant, that's what we get? Isn't that, again, a lot less clunky? Even save some ink. I know you see it. I know you see it. I know you see it. Or once you see it, you will not unsee it. We want that to be so. What? Why do we have this clunky version? It's in the form of y equals mx plus b. Why would we want that? Go, sir. Why? What does that help us with?
The slope of A over time, right? So then that would be magnifying graph out, and then you feel it will find the rate.
Would that tell us the rate? Definitely. And this is what it's going to tell us. So remember, we saw this the first day that if A is our reactant, as the reaction proceeds, rate changes. So if you're given concentration versus time of a reactant, we just know it's going to be that shape. That doesn't tell us the order. But if we're given data of concentration and time, couldn't we just find the natural log of each of those concentrations per time? And ding, 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 if we get negative slope, then what do we know about our reactant? We got this equation by integrating this rate law for a first order reactant. A first order reactant. Well, first order reactant is not going to show itself if we just graph concentration versus time, but that's what we measure in lab. That's what we measure. Well, could we just find the natural log of the concentrations, graph it? If it is linear, we know it's first order because it matches what came from this equation. If it's not, so the other thing that it could look like is curve. Oh, shoot, sorry, is a curve. Well, then no go. It's not first order. So graphing natural log of reactant versus time confirms first order. Confirms reactant. Okay, but can I ask you another question, David? Oh, are you going to tell me? When? Yeah. Yeah. What does your slope tell you? It reveals the rate constant. And you're absolutely correct, sir. Because natural log, we're looking right for the exponent, so no unit per time. So whatever this is, and so the unit for first order is just per unit of time, or whatever the time is to -1. Yes? Yes. I'm just gonna make shields that we can just put on our faces with a big smile. So I just can pretend we're smiling at all this great information instead of what I see in front of me. Beautiful, amazingly talented students, but no expression. Okay. So, can we do first example? Now, looking at this data, take a look. Concentration and time. Concentration and time. Would we apply the method of initial rate here? Do we see like, oh, okay, we decreased that in half. What impact did that have on the rate? No, right? Very different information than here. We see that. So if you are given concentration and time, and it asks us, oh, it's asking us to verify its first order. Well, then we know to verify its first order, we need to graph natural log of N205 versus our time. All right, and if it's okay with you, I'm just going to share and our slope is negative 6.93 times 10 to the minus third per second. So given data, we have to know what step we take with the given data. So if you're given concentrations and time, you need to graph. You can absolutely graph using your calculators. And if anyone needs help with that, just let us know, lean on a friend. You will not have to graph on an assessment. I will provide you the graphs because I'm not testing, can you make a graph? I'm testing, do we know what graph can give us what information we need? So I'll keep reminding us of that and reminding us of that. But for unit assignment and in-class work and lab work, we need to know how to create a graph with our, oh, you don't have to use your calculator, use graphical analysis. Anyway, all right. So it's asking calculate the value of the rate constant. Well, here, of course, because of integrated rate law for first order reactant, we know our slope is negative K, then the K value is 6.93 times 10 to the minus third per second. All right. Rishi, this example here, using the data above, calculate N205 at 150 seconds after the start. Whenever you know it's first order, you can apply this whenever you need it, if you need it. Will this give us what we want? What will we solve for? Sure, that could be our goal. And then we can do the e to the x, undo the natural log. Sure. And we have everything else we need. So if we're solving for this, and we'll plug in our K. And we're looking for 150 seconds. And our initial concentration is 0.1. And we know how to do the e to the x. Don't worry. There's different sig fig rules with natural logs and logs. We don't have to worry about that now. Given that 150 seconds, if you reported 2 significant figures, more than fine. More than fine. Now, before we break for homeroom, does this answer make sense? It takes a moment to check. 150 seconds. So, right between there and there, we found that the concentration is 0.0369 molar. Is that sensical? Absolutely. If you need any help with that, just let me know. Okie dokie.